in mathematics, and we have scientific evidence that this is the most beautiful equation. In 2014, University College London invited mathematicians to come, and they hooked them up to brain scanner, fMRI machines. And so they're scanning the brains of these mathematicians and showing them equations. And the mathematicians would say, oh, that's a beautiful equation, or that's an ugly equation. And they noticed that when they viewed a beautiful equation, the emotional center of the brain lit up. And not just the logical center, the emotional center. So the same way that you'd respond to seeing a beautiful painting or listening to an incredible piece of music, these mathematicians would respond to beautiful equations. And the mathematicians said that this is the most beautiful equation. E to the I pi plus 1 equals 0. Okay, why is this so beautiful? Let me try and help you appreciate the beauty of this. Well, one's a pretty basic idea. You know, if you want to count things, you have 1 table, 2 table, 3 tables. You know, nature kind of forces this idea of 1 upon us, and the counting numbers, 1, 2, 3, and then 0. Well, that's kind of maybe a little bit more interesting. What does it mean to have 0 tables, right? I guess there's no tables, but 0 is kind of subtle. In the history of math, it took us a while to develop the idea of 0, but kind of still, you can see where it comes from, the idea of counting. But then you get things more interesting, things like pi. Pi comes from thinking about circles. And it's this basic fact that if you take any circle, and you measure the circumference, and you measure the diameter, and you compare the two, the circumference is always pi times the diameter. Any circle, a big circle, a small circle, it always comes out to be pi. And pi is kind of a strange number. It's not a whole number like 3. It's a little bit more than 3, but it's irrational. It goes on forever. 3.14159265358, so on and on and on and on forever. So pi is a little bit of a strange and mysterious number, but it comes from thinking about circles. And then next to pi, we have this other number in this equation. It's e to the I times pi plus 1 equals 0. So what is I? Well, this isn't thinking about circles, but thinking about squares. So you have a square and it has side length, say, 2. And so if its side length is 2, then the area is going to be 2 times 2, or 4. So we say 2 squared is 4. Or if the side length is 3, we'd say the area is 3 times 3, or 9. So 3 squared is 9. And so on. You know, what squared is 16? Well, 4 squared is 16. Continue to think about it. But the mathematicians were trying to think about just, you know, can you ever square something to get -1? This was about the 1500s. And, you know, if you do -1 times -1, well, a negative times a negative is a positive. It's +1. So that doesn't work. So they made up a number. They just made up I. So mathematicians created the number I, and they said, let's just make I be this number where I times I equals -1. It's just a made-up number. It's called an imaginary number. Originally, the word imaginary was kind of making fun of these numbers. Like, what are you guys doing, making up numbers like I? You know, you're just cheating, you're just playing games. But the mathematicians thought it was pretty neat, so they did it anyway. And then the last thing you have here is E. So E comes from, it's fundamental in calculus. It's a little bit more sophisticated of a notion, but it's related to this idea of taking limits as things go off to infinity. It's connected to the idea of derivative and integral. It comes out to be a number. It's between 2 and 3. It's 2.7182818, so on and so on. So it's kind of like pi. It's irrational. It's kind of a strange number, but it's foundational to the calculus. But now look at this equation again. 1 is the number from counting. 0 is a little bit more interesting number, but still kind of related to the idea of counting, the idea of existence. Pi comes from geometry, thinking about shapes. I, well, squares, but solving equations. It's solving something squared equals this. X squared equals this. If x squared equals -1, what is x? So I comes from solving equations. And then E comes from the calculus. In the 1700s, a mathematician by the name of Euler came along, and he showed that all of these things in math, from all these very different areas of math, from thinking about circles to solving equations to doing calculus, they all fit together in this one beautiful equation. So we call this Euler's identity. And mathematics is like this all the time. You have an idea that comes up in the context of circles, and then suddenly pi is found to relate to something over here. And how do these things connect? How do they relate? How does I show up in here? I thought we made this thing up, but apparently I fits in here like we were supposed to make up the idea I. So somehow it fits into this equation. How do all these things fit together? Why does math work? And this is the question that mathematicians have thought about quite a bit. And philosophers of science, philosophers of math have wondered, why does math work? One person who mused about this in the 20th century was the Nobel laureate Eugene Wigner. He was a theoretical physicist, mathematician, and this was his reflection. He noticed that throughout history, the great mathematicians, he said they fully, almost ruthlessly exploit the domain of permissible reasoning and skirts the impermissible. They make up stuff like I. They just come up with these ideas, and it's like, it doesn't seem like they should be allowed to do that, but there's really pushing boundaries, coming up with new ideas. But then he says that this recklessness of the mathematician, that it does not lead him into a morass of contradictions, is a miracle in itself. It's incredible that the mathematicians thinking about these ideas can actually come up with a harmonious body of thought. There's not contradictions in it. They all fit together. But then he goes on to say, certainly, it is hard to believe that our reasoning power, the power to do mathematics, was brought by Darwin's process of natural selection to the perfection which it seems to possess. Here, the Nobel-winning laureate Eugene Wigner, he's reflecting, he's thinking, how is this possible? How are we able to do mathematics and come up with this incredible body of knowledge if we were simply the process of natural selection? After all, if it was simply the process of survival of the fittest, it would make sense why we're pretty good at surviving, but it doesn't make sense why we'd be able to find truth. Why would our brains be equipped to do mathematics? I can tell you that doing mathematics doesn't help you survive very well, especially this kind of mathematics. So why is it that our brains have this ability? What explains that? He says, I don't see how Darwinian theory, how natural selection is a sufficient explanation for our ability to do mathematics. But there's a further mystery that Wigner goes on to reflect upon. And it's not just that we can do mathematics, but it's actually that mathematics explains the universe around us. First of all, the fact that the universe makes sense is in itself a mystery. Albert Einstein said that the most incomprehensible thing about the universe is that it is comprehensible, that we can understand it. Back to that problem, if we're just here to survive, why can't we understand the cosmos in this deep way? Albert Einstein, the stuff he was doing is counterintuitive. His insights about the nature and fabric of reality, about how time works, it doesn't seem to make sense. Why are we able? It's very counterintuitive. It's not the intuition that we have around here. But he says, but I believe it's true because that's what the math says. He was following the equations of Maxwell. He was just deducing facts from these equations to give him his key insights to the nature of the fabric. It didn't seem intuitive, but then we did experiments and it checked out. Time and time again, mathematics suggests something about the nature of reality. It doesn't seem right. It seems kind of counterintuitive. But we test it and it checks out. We are built, for some reason, somehow, to be able to access these deep insights to the world around us. Things like the recent discovery of the Higgs boson. I was reading this article a couple of years back that was saying, now that we discovered the Higgs boson, and this was in the laboratory at CERN, this giant particle accelerator, they were saying, now that we have found the Higgs, we've replaced God. The Higgs boson is the God particle. We can now explain the universe so well, we don't have any need for God. And I was reading this, and I was just amazed. It's like, wait a second. You're saying that some guy sat down, looked at the standard model for physics, did some math, came to a prediction that this particle should exist, spent $10 billion, the governments of Europe, building the particle accelerator at CERN, found it, incredibly, the math checked out, and you're saying that this proves we don't need God? If anything, there seems to be a profound mystery here. Why are we able to do science? Why are we able to do mathematics? And I want to suggest that every mathematical insight, every scientific discovery is actually evidence for God. At least historically, this is how it was understood. Eugene Wigner goes on and he says that this is a miracle. Notice that language. He says, the miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve. The fact that math works to explain the universe, the fact that we're built to understand and study the world around us is an incredible gift. It's a miracle. That is the modern day miracle. Science itself is a miracle. So how did we come to this place that we are now, being able to do science and understand the world around us? Notice what Morris Klein writes in his History of Mathematics. He notes that this thought, this idea that all the phenomena of motion, even all the phenomena of the natural world, should follow one set of principles. It seems like some grandiose, inordinate idea. But he says that this idea occurred very naturally to the religious mathematicians of the 17th century. God had designed the universe, and it was to be expected that all phenomena of nature would follow one master plan. You see, this wasn't the understanding of the Greeks. The Greeks had this conception that the universe followed one set of worlds of the cosmos, that things went around, and here on Earth, things came down, and this was Aristotelian worldview, and it was very diverted, breaking up the universe to here's how things move in the heavens, here's how things move on Earth. But then Newton comes along. Newton, a devoted Christian, and he says, no, I believe that there's one God. I believe there's a creator God who created both heaven and earth. And since I believe there's a God who created both heaven and earth, I believe there should be one explanation to explain both the movement of why the apple falls on my head and how the bodies move in the heavens. And therefore he formulates his law of gravity. And Newton, while he was doing this, while he was putting forward these scientific principles, he would write to his friends and he would say, my greatest joy in doing this work, in producing, for instance, the Mathematica Principia, he said, my greatest joy in doing this is that it might lead thinking men to consider belief in a deity. That when people see this, when they see the coherence of the universe, they might see there's one mind behind it. They might come to believe that. That modern science was built on the foundation of scientists who believed there was law in nature precisely because they believed in a lawgiver. This is simply a historical fact. The doctrine of creation, the belief that the creation is ordered, there's a creator who ordered the law around us. And this idea that we are made in his image so we can understand that creation, that is the foundation for modern science. You know, Christianity, though, the biblical narrative, it offers a whole lot more than simply an explanation for why we can do science, why we can understand the world around us. Because when we begin to think about and probe the world around us, we begin to notice things. We notice the problem of evil. We notice the widespread suffering. We notice big questions like, wait, why am I here? What's my purpose? Is it, what's the point of all this knowledge? Where's the universe heading? And if you simply take an entirely naturalistic worldview, you'd come to the conclusion that the universe will continue to expand, and eventually there'll be some kind of heat death of the universe, all energy will be used up, all life will cease to exist. It's kind of a gloom picture. But the Christian worldview, the biblical worldview, offers a much richer picture. A picture of a God that not only explains why there is creation, why there's order, why we can make sense of the world around us, but actually a picture of a God who loves us and cares for us and desires to be in relationship with us. Ellen White, in the book Education, on page 132, shares that the hand that sustains the world in space, the hand that holds in the orderly arrangement and tireless activity all things throughout the universe of God, is the same hand that was nailed to the cross for us. That somehow the biblical narrative is both able to explain modern science and the success of mathematics and physics and these other fields, but it goes beyond that. It explains meaning, it explains significance. This is why I take the biblical account seriously, because of its incredible explanatory value, both as a mathematician for me to do mathematics, but also to explain life and how we make sense of it, to explain where I'm going and where I've come from and why I'm here. I want to invite you too to take seriously the biblical account, to consider the person of Jesus. At times trying to figure out God, it can be tough, but I believe in Jesus we see a clear revelation of what God is like. I was mentioning before this equation, this beautiful equation, e to the I pi plus 1 equals 0. And the neat thing about this equation is it seemed like mathematicians were just playing games and they came up with this idea of I. But then they see this and they're like, wow, this is a beautiful thing. This is worth holding on to. And it wasn't until a couple hundred years later that it turned out that actually it's essential for us to understand the universe is we need imaginary numbers. We came up with imaginary numbers just as a game. We thought they were beautiful. We thought they were interesting. But in fact, they're essential to understand the world around us. Quantum mechanics can't be done without imaginary numbers. Things like Euler identity is essential to doing physics. And doing math has taught me something. Pursuing beauty and pursuing truth are quite interrelated. The mathematician seeks results simply because he finds them beautiful. But then the physicist says, hey, actually that's true. That describes the world around me. The world is somehow both beautiful and true, and these things are wrapped together. And in Scripture, I find a similar revelation. That in the person of Jesus, I find the most beautiful revelation of who God is. But as well, he is the embodiment of truth. That beauty and truth are somehow wrapped together in the person of Christ. And somehow this is the best way for us to make sense of the world around us.
Thank you so much, Anthony, for your insights into imaginary numbers and the beauty that we can see in them. We're going to conclude our symposium with a